we should be able to get through it all. Let me share my screen with you. All right. So okay, so chapter 7 is all on gases and the gas laws. Gases, because of their just nature, they follow a really specific set of rules and equations that are pretty easy to follow. I think you might find this chapter a little refreshing after all the stoichiometry stuff. So extra long straws. I don't know if when you were a kid, if you ever like chained a bunch of plastic straws together to see how long of a straw you could have. Is there a limit to how long your straw could be, even if you were very, very good at slurping up soda? There is actually a limit. At sea level, it would be about 10.3 meters or 34 feet. So why is that the case? Well, what's happening in a straw is the atmosphere is exerting a pressure. So if we look here, we have a surface, and the surface can be a solid or a liquid. And we have gas molecules bumping into that surface. Okay. And the more gas you have, the more collisions you'll have, the more pressure you'll have. That's why as you go up in sea level, pressure decreases because you have less gas molecules hitting the same area. At sea level, we have, as far as pressure is concerned, we have 101,325 newtons. And if you've taken physics, newtons is a unit that you see a lot in physics per meter squared being an area. Well, looking at this cup here of orange pop, there is a pressure that's being exerted from the air around. And that pressure is pushing down on the liquid outside of the straw as well as inside of the straw. So we've got an equal pressure, so the level of the liquid stays the same. When we suck on the straw, what we're actually doing is removing air molecules from the straw. And that causes a lower pressure. That decrease in pressure, if we sort of see this as like a tug of war between these two vector arrows, this arrow is stronger than this little arrow. The little arrows, because we have a decreased pressure, so the fluid is allowed to rush in. At some point, you've removed so much of the gas molecules that the liquid reaches your mouth. Well, if we were at sea level, and let's say we had that straw connected to, like, it was like a perfect seal and it was connected to an awesome vacuum. The only height that we could reach with our soda pop liquid would be 10.3 meters because the pressure on the outside is only so strong to push down. If we were in like if we were on Venus or something where we have a higher pressure, more gases, that liquid could potentially go higher. So it's sort of like a random opening, but so gases in general follow this thing called the kinetic molecular theory. It's a model for gases. And this model helps us to predict the behavior for most gases under most conditions. Like all models, the kinetic molecular theory will break down in certain situations, specifically if you have a gas that is really, really cold, or you have a gas that's under a very, very high pressure, something where you force the gas molecules together, they kind of start to stick to each other. But if we're in standard situation, which we'll focus most of our time on, it follows these really nifty rules. So a couple things related to the kinetic molecular theory. One, a gas is a collection of particles that are moving in constant straight line motion. Okay, so they're making, think of them as like billiard balls on a pool table. You hit it and it moves in a straight line. They don't swivel around. They don't take, the long path home. They're going A to B. These gas particles don't interact with each other. So in solids and in liquids, because they're compact in such a small volume, the particles will, or whether it's atoms or molecules, will actually interact with each other, which will give them this sort of quote unquote like sticky quality, which allows the molecules to clump together. Gases don't do that. Gases are moving so fast and they have so much space between the molecules that they don't interact with each other. And if they do happen to bump into each other, again, back to that billiard ball collision idea, they will hit and then they will separate, kind of move like in the other direction from each other. So then we've got a lot of space between the particles compared to the size of the particles themselves. You kind of already know that about gases. And then the other thing, the speed of the particles increases with an increasing temperature. So if I increase the temperature, you will increase these particles, their velocity. This is sort of saying the same thing. One thing I want to note, the average kinetic energy, which is the energy of motion, so this is the speed, the velocity of the gas particles, is proportional to the temperature in kelvins. A lot of the equations that we're going to use today, we need to make sure we convert to Kelvin. Okay, the equations don't like being in Celsius. There's one that's okay with Celsius, but most of them like you to convert to Kelvin. So this model helps us predict and is consistent with a lot of the properties that we already know of gases. So we know gases are compressible because they have a lot of empty space. Gases will assume the shape and volume of their container. So think about, having an image here. We have a mason jar full of gas particles. If I open this canister, because those gas particles are moving in straight motions and they're not attracted to each other, if I open the top, it's just the gas is gonna expand and disperse into the dimensions of whatever room we're in. That isn't the case for solids or liquids. If this was a container filled with liquid, like water, and I opened the top, the liquid is just gonna sit at the bottom because the liquid particles are interacting with each other. Here, that isn't happening. So the gas will always expand to fill whatever container it happens to be in, whether that's the small container, a classroom, a building, the atmosphere. It will always sort of disperse its way out. And then gases have low densities in comparisons to liquids and solids. So yeah, 1 can of pop converted into a gaseous form would equate to 1,700 cans of soda as far as the volume is concerned. Okay, so when we're talking about gases, we can't really talk about gases without talking about their pressure. Pressure is the result of the collision between the atoms or molecules in a gas and the surrounding surface. Because of pressure or pressure differentials, we can drink out of straws, we can inflate basketballs, air moves in and out of our lungs, and we have these really interesting weather patterns. So what are the units of pressure? I guess the simplest equation for pressure equals force over area. So exerting some amount of force over a specific area. So if the force is great and the area is small, high pressure. If the force is small and the area is great, low pressure. Here are 2 examples of gases in closed containers. The top one has less gas particles in it, which means there's going to be less collisions and hence less force. So this is going to have a lower pressure. This jar down here has the same area. It's the exact same shape, but it has, looks like twice as many air, or we don't know if it's air, but it has twice as many particles to it. So we have twice as many collisions. So our pressure will be twice the amount here. So the units for pressure, the simplest one we use quite a bit is an ATM, or an atmosphere. And that is it's a very human-based scale. 1 ATM is related to the pressure that we experience on Earth at sea level. Okay, so unless you guys are like secretly on vacation somewhere and at the beach, here in Asheville, we are slightly less than 1 ATM. Not a whole lot, but a little bit less because we're up in elevation. So there's a little bit less air here than there is at sea level. The SI unit for pressure is going to be the Pascal, PA. And this is defined as a Newton per meter squared. So 1 Pascal would be 1 Newton per meter squared. The Pascal is not a big unit. It's a really tiny unit. If we talk about the relationship between an ATM and a Pascal, 1 ATM is equivalent to 1,000 101,325 pascals. So a lot of these pascals in an ATM. There's another unit that we use for pressure, and that's mmHgs, or millimeters of mercury. If you are like a weather nerd, which I kind of am, and you like to look at like weather patterns and stuff like that, or look at pressure systems on a map, they usually give the pressure of the atmosphere in mmHgs. Now, what does it mean? Well, a millimeter of mercury in relationship to like if we were sitting at sea level. So if we were sitting at sea level and we had liquid mercury and a vacuum tube, the amount of atmospheric pressure at sea level, which is 1 atm, would allow mercury to move up the glass tube 760 mm's, or 760 millimeters. So at 1 atm, or at sea level, it's equivalent to 760 mmHgs. This one we tend to convert a lot between, okay? So you definitely wanna know that one. There's another pressure that we use called a torr. A torr and an mmHg are the same thing. It's a 1-to-1 ratio. They're not the same thing, but their magnitude is the same thing. This one I don't really use ever, an ATM conversion to inches of mercury. Don't really use that, but this one is kind of useful. 1 ATM is equivalent to 14.7 PSIs, and you might have heard of PSI. That's a very like American/British unit, pounds per square inch. So if you've ever like filled up a bike tire and things like that, you use PSI. So depending on the type of bike you have, whether it's a mountain bike or a road bike, you can range anywhere from like 50, 60 PSI to like in the low hundreds. So there we go. We've got a bunch of units. I want you guys to convert. We'll just do one of these just so you guys can bring back that dimensional analysis. So let's say that we're given 2.3 ATMs. So we're at like a high pressure environment. I want you to find this in millimeters of mercury and torr. I'll just give you guys a minute and a half for that. That's a pretty simple conversion. All right, so we are given information in ATM and we want to find millimeters of mercury. So 1 ATM is equivalent to 760 millimeters of mercury. It says, hey, that is exact. So we take our 2.3 decimal there, ATM. The relationship is going to be 1 ATM for every 760 mmHgs. That allows the ATMs to cancel. So we end up taking 2.3 and multiplying it by 760. I only gave you guys 2 sig figs, so I'm going to round this to 1700 mmHgs. As far as the torr is concerned, the torr and the mmHg are an exact replica. So I can say that it's 1700 torr as well. So just simple conversion, nothing too dramatic. All right, what is this about? Why are airplanes pressurized? Okay, your airplanes are pressurized so that they can pack more oxygen into a given space. When you move up above 25,000 feet, the pressure is below 0.5 ATM, which means you have a much lower atmospheric pressure than what you're used to and your body's used to. In that case, you receive less oxygen and you'd pass out. So they pressurize the cabin. Okay, so the next part of this, first part was a little bit more concept based. The next part is just going to be a series of equations. And I'm not a stickler on like, I'm not going to test you and be like, which one of these is Boyle's law? But you do need to know which equation to use in which given problem. So this first one is called Boyle's law. In Boyle's law, we're going to be looking at the relationship between pressure and volume. Okay. We're going to assume that the temperature and the amount of gas stays constant or consistent. Sometimes I think it helps to write like this overall general equation for everything we're talking about. V1, actually P1, V1 over N1, T1 is equal to P2, V2 over N2, T2. Okay, so sort of think of this as your master equation, and we can derive all the other equations that we need by crossing out things in this. So if the temperature and the amount of the gas are constant, that means I can ignore temperature and amount. And actually, let me tell you what all these things are. So the ones refer to an initial set of parameters. So we're going to have a gas at like a given pressure, a given volume, a given temperature. And what's going to happen is there's going to be some sort of change. Okay, we're going to lower the pressure, or we're going to increase the temperature. We're going to do something to mess with the gas. And this will be our final parameters. So it's a starting and an ending. P is for pressure. V is for volume. Pressure and volume can be in whatever units you want. They just have to be in the same. So if it's like ATM on one side, it has to be ATM on the other. Volume, same thing. If it's liters, it just needs to be liters on both sides. If it's milliliters, it just needs to be milliliters on both sides. Down here, N is talking about the amount of gas. That has to be in moles, okay? No exceptions. N has to be in moles. T is talking about temperature. Temperature has to be in Kelvin. The equation will not work. The relationships will not work if you're in Celsius or Fahrenheit. So just make sure to convert to Kelvin. Now, in this first set, Boyle's law, we aren't talking about temperature and we aren't talking about amount of gas. We're saying that those are staying consistent. So what I can do with my master equation here is cross those out. So I can cross them out for amount and for temperature because there's no change there. And what I'm left with is Boyle's law, which is P1 V1 equals P2 V2, or the initial pressure times the initial volume will always equal the final pressure times the final volume. 4 variables for this equation, 1, 2, 3, 4. How many are you going to get? You'll get 3, and you'll have to solve for the 4th one. P and V in this equation are inversely related. So what that means is that as pressure increases, volume decreases. Or if volume increases, pressure decreases. As one goes up, the other goes down. So this is Boyle's law in a nutshell. Let's move forward. Here is a good example of Boyle's law. So upstroke, on the upstroke, the increasing volume causes a decrease in the internal pressure. This draws air into the cylinder. On the downstroke, we decrease the volume, right, which causes an increase in internal pressure. So that's why it can feel really hard at the end when you're, if you're blowing up a tire or something at the very end of the stroke, because you've compressed all that gas, which then forces it through the tube and into your whatever you're inflating. So this here just means that volume is inversely related to pressure. So as this number gets bigger because it's below a fraction bar, this number gets smaller and vice versa. Okay, yada, 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 yada. Anna talks about the same thing. All right, keep moving. Okay, because we're covering the whole chapter, so we don't need to get bogged down in details. All right, let's look at this problem here. So a cylinder equipped with a movable piston has an applied pressure of 4 atms and a volume of 6 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? So I'll walk you guys through this one and then I'll have you do one on your own. So the first thing you need to do is know that you need to use Boyle's law, or whatever law talks about these things. I don't care if you know the name of it. What you can see here is that there's units of pressure and there's units of volume. All right. And I can see that there's a change, right? At one point, I'm at 4 ATMs. At another point, I'm at 1 ATM. So I know that I'm going to need to use a P1 V1 equals P2 V2. So it might help you to just write that out. P1 V1 equals P2 V2. Then you want to organize your information. So remember, the ones are your initials. The twos are your final. I feel like this is really actually quite easy, but what happens is students will miss or mess up going from the word problem into the correct position. And if they're not in the correct position in the equation, it will give you the wrong answer. So our initial pressure is our starting pressure. All right, we've got 4 ATMs. So 4.0 ATMs. Our initial volume is 6 liters, 6.0 liters. Get in the habit of when you see ATM, that's talking about pressure, okay? When you see liters, milliliters, inches cubed, meters cubed, that's talking about volume. My final pressure is 1 ATM. And it says, hey, what's the final volume? That's what we're trying to solve for, V2. So when looking at my equation, I need to get V2 by itself. I need to isolate the variable. So I want to get P2 to the other side. The way that I do that is I do whatever the opposite operation it is here. So here it's a multiplier, so I'm going to divide it by P2. If I do that, P2's cancel. Whatever I do on this side, I have to do on this side, so I get P2 over here. So my V2 equation is going to be P1 times V1 divided by P2. And it's so easy to mix up those little subscripts. Don't do it, because you want to make sure you're plugging the right information in the right place. So P1 is 4 ATMs, 4.0 ATMs. I always add my units because it lets me know that things are canceling correctly. My initial volume is 6 liters, 6.0 liters. All right. And then my P2, my final pressure is 1 ATM, 1.0 ATMs. So what happens is the ATM unit will cancel and you'll just be left with a unit of liter, which is perfect because we're solving a volume. So we'd want it in liter. So you plug that into your calculator and you get 4 times 6 divided by 1, or 24 liters. This whole thing does not work with solids and liquids. Gases are the only thing that have this really nice quality to them. Does this make sense? Well, think about what we did. If we take the pressure and we decrease it by a factor of 4, I'm going to increase my volume by a factor of 4. Okay, so this is a fourth and this is 4 times as big. So we now have been able to figure out the final volume. My pressure went down, the gas expands. So I'll have you guys do one. All right. I want to word this. What is the volume of 22.6 liters of a gas? The volume of 22.6 liters of a gas that changed pressure from 1 ATM to 0.34 ATMs. And let's make that not just 1. Let's do it as 1.0 so you guys have more than 1 second. Okay, so what is the volume of 22.6 liters of a gas that changed pressure from 1 ATM to 0.34 ATMs? give you two minutes or so for that. Okay, so very similar setup for this problem as the last one, worded slightly differently, but we're talking about volumes and pressures. We're not, temperature doesn't come into play and amount of gas doesn't come into play. So we'll use Boyle's law, V1, or rather P1, V1 equals P2, V2. Again, it looks like we're going to be solving for the final volume. That's not always the case. Sometimes you'll solve for the final pressure. Sometimes you could solve for the initial pressure or volume, depending on the problem. So V2 is going to equal my initial pressure times my initial volume divided by we're solving for volume. Yes. So final pressure. So our initial pressure is 1 atm. Our initial volume is 22.6 liters. And our final pressure is 0.34 atms. So again, my pressure is decreasing. If my pressure is decreasing, I would expect my volume to increase. ATMs cancel. We only have 2 sig figs, so we do get 66 liters is our final answer. Just double check, 22.6 divided by 0.34. Yeah, 66.47, so we'd round to 66 with 2 sig figs. Hopefully that's refreshing after the last chapter. We're just going to kind of do more of this. So let's go to Charles' law. Charles' law Okay. So in Charles' law, we're going to be looking at volume and temperature. So why does a hot air balloon rise? Hot air rises because the volume of the gas sample at constant pressure increases with increasing temperature. Let's look at our master equation, which we said was P1 times V1 over N1 times T1 equals same thing, but use 2's. 2V2, N2, T2. So when talking about Charles' law, we're going to keep our pressure consistent, so I can ignore pressure, and we're going to keep the amount of gas consistent. So we're going to cross out the ends. So what we get is V1 divided by T1 is equal to V2 divided by T2. That becomes our Charles' law. And volume and temperature, I know it doesn't look like it in the equation, but it is directly related. So as the volume increases, the temperature increases, or vice versa. If the temperature increases, the volume increases. Let's look at, so if we have like a balloon filled with air, and we don't go up a mountain or down into the ocean, we stay at the same pressure and we don't change the amount of air because we've got it sealed off. If I take that balloon and I put it in ice water, the balloon will appear to shrivel. It's not actually like shriveling because there's less gas. It's shriveling because the little gas molecules come closer together. I can take that same balloon and I can put it in boiling water and it will look as though the balloon is growing. And it's not growing because there's more gas in it. It's sealed off. It's growing because the gas particles have more energy, can kinetic energy, so they're moving faster and they expand. This, so this is why hot air balloons work. Okay, we heat the gas up. The gas is relatively contained in here. It's the same amount of gas. We heat it up, it's going to expand. As it expands, it becomes a lower density than the air around it, and it rises. Temperature has to be in Kelvin when we're using this equation. This equation does not like Celsius. It doesn't like negative numbers. So if we were to draw a graph and look at the volume of the gas versus the temperature, okay? Well, like we said, if we cool the gas, it takes up a lower volume, right? Smaller volume. We shrink the balloon in the ice. At some point, we get so cold, we approach what's called absolute zero, which is negative 273 Celsius or 0 degrees Kelvin. There's nothing colder than this. At 0 degrees Kelvin, all molecules cease any sort of motion, and a gas actually approaches a volume of 0. We never actually approach absolute Kelvin, just like we can never actually approach a 0 volume. We can't get any colder than this, though. If we got colder than this, our gas volume would end up taking up negative space, which doesn't make a whole lot of sense. So don't want any numbers as far as temperature is concerned below absolute 0. Doesn't exist anyway. Okay, so Charles' law. So there's our Charles' law. Again, you can derive it from that master equation. So if you have the master equation, just cross out what you don't need and work from there. V1 divided by T1 equals V2 divided by T2. Again, the ones are talking about initial parameters. The two are talking about final parameters. So I'm going to have you guys work on this one on your own. This is a Charles' law problem. A sample of gas has a volume of 2.8 liters at an unknown temperature. When the sample is submerged in ice water, which is at 0 degrees Celsius, and you can assume then the gas is also at that temperature, its volume decreases to 2.57 liters. What is the initial temperature in kelvins and in degrees Celsius? You assume a constant pressure. So you do need to use Charles' law for this, but make sure, just notice this is in 0 degrees Celsius. Those equations don't work for Celsius, so make sure you convert to Kelvin first, okay? Don't put Celsius into the equation. So I'll give you guys 2 minutes for that because the setup is very similar to Boyle's law. It's just a new equation. All right, so again, if you were to see this problem on a test, what you're seeing is it's discussing volume and it's talking about temperature. It doesn't bring into mind pressure or amount, so Charles' law is the one that we're going to want to use. So our initial volume is 2.8 liters. Our final volume is 2.57 liters, so it actually shrunk. My final temperature is 0 degrees Celsius. So we're trying to find the initial temperature, T1. Now, the equation will only work if these are in Kelvin. I mean, look at what happens anyway. If you were to even plug 0 in as your final temperature, you're going to get an error message because it's below the fraction bar. So we need to convert temperature into Kelvin. We just take 0 and add 273 to it, which gets us into a positive value, which we like. So we've got 273 for our final temperature. When we isolate the variable here, we wanted to solve for T1. This sometimes throws people because they go, oh, well, V1's on the top here. So I'm going to divide by V1 and divide by V1. That's fine, but that doesn't give you T1. That gives you 1 over T1. So then you need to flip-flop those to get the correct equation. So 1 over T1 will equal this V2, T2, V1. T1, which is what we want. We don't want 1 over T1. T1 will equal the inverse of that, T2 over V1 over V2. And I see that mistake happen quite often. So just make sure you're isolating variables correctly with that. So here is our equation. Both of the volumes are in liters, so we're good there. We've got this thing in Kelvin. It's going to pop out a number in Kelvin. So we get 297 Kelvin. Now the problem said, hey, I also want to know what it is in degrees Celsius. So if you want to convert it back to degrees Celsius, you just subtract 273 and you get 24 degrees Celsius. Now, if you're like, well, why didn't I, if it's giving me Celsius and it's asking for Celsius, why don't I just plug Celsius in? It won't work. It will not work. So make sure, if they give you Celsius, you convert it to Kelvin, you run it through the equation, you get your Kelvin, then you convert back to Celsius. It's the only way to use this. Any questions on this or Charles' law or isolating variables? If you're like, oh, I don't remember how to isolate a variable, or any comments or anything like that. I hope that this feels a little bit simpler than what we've done in the past. It's kind of, basic algebra. If you have the equations, you just plug and chug. Okay, so let's go on to another law, what we have known as the combined gas law. So that's where we take Charles' law and Boyle's law and sort of smoosh them together. Or we have changes in pressure and volume and temperature. So remember, our original master equation would also have that N1 and N2 value. Well, we're just saying, hey, amount stays the same, but all the other stuff is changing. So we cross that out and we're left with this combined gas law. Notice there are 6 variables here. So you need to shuffle and organize 5 given variables and you'll solve for the 6th one. That's how basic algebra always is. When you have an equation, you're given 1 less than the total number of variables. If you're missing 2 of the variables, that's when you would use like a graphing calculator and you'd have to use a little bit more advanced math. Okay, so here is a problem that you get to work through. I will write the combined gas law up top here, just so you have it. P1 V1 over T1 equals P2 V2 over T2. Okay, and in this problem, it says, hey, a gas has an initial volume of 158 milliliters, a pressure of 735 mmHgs, and a temperature of 34 degrees Celsius. If the gas is compressed to 108 milliliters and it's also heated to 85 degrees Celsius, what is the final pressure in mmHgs? So because this is milliliter and this is milliliter, keep your volume in milliliter. All right. And because pressure is given to you in mmHgs, keep it in that because it wants the ending in mmHgs. Temperature, I want you to fiddle with. Celsius can't get near this equation. Okay. So this one I'll give you guys like 3-4 minutes for. It requires a little bit more plug and chugging. Okay, so Again, how do you know you use the combined gas law? Outside of it tells you here at the very top, but on a test it doesn't. These are all going to be sort of jumbled together. So you can see that there is a reference to volume, a reference to change in temperature, and a reference to change in pressure. So, you know, and then also there are 5 given pieces of information. So you'll be solving for a 6th. So all the units are good. We can keep pressure. We can keep we can keep pressure in millimeters mercury. We can keep our volume in milliliters. We do have to shift our temperatures though. If we isolate for P2, so we want the final pressure. I need to get rid of these 2 things, not get rid of them. I need to move them to the other side. So I'm going to multiply this thing by whatever the inverse of this. I'm going to put the volume on the bottom. That allows this to cancel. And I'm going to put the temperature on the top. That allows this to cancel. Whatever I do here, I do over here. So I need to have the V2 on the bottom and the T2 on the top. Important to be able to isolate variables. All right. So there is our final isolated equation. We convert the temperatures. T1, which was 34 degrees Celsius, now becomes 307 Kelvin. And T2, which was 85, becomes 385 Kelvin. So we plug this into our equation and you'll see milliliters cancel and Kelvin cancel, and we'll be left with millimeters of mercury. And we get 1.25 times 10 to the 3rd millimeters of mercury. Don't get freaked out by scientific notation. We can undo that, move the decimal out 3 places. It's 1,250 mmHgs. So in the end, our pressure went up. Let's think about what we did, right? We increased the temperature. Actually, I don't remember, we gotta go back. So we increased our temperature and we decreased our volume. So yeah, I would definitely expect the pressure would go up because we're making it hotter and we're forcing it into a smaller space. So it should go up. Okay, we've got one more of these change in laws, and that's Avogadro's law. There's actually another one called Guy-Lusac's law, but we won't cover that one. But Avogadro's law, and remember Avogadro, like Avogadro's number, has to do with moles. So this is going to relate the volume of a gas to the number of moles. It's a direct relationship. It says, hey, the volume is going to go up if you have more moles of a gas, if you have more of a gas. That's common sense, I feel like. When you blow up a balloon, why does the balloon get bigger? Because it has more air. You've put more moles of air, CO2, whatever you're breathing out, into that balloon, and its volume has increased. So these guys are directly related. As volume goes up, amount goes up, and it doesn't give us the equation. And these slides drive me crazy, but let's go back to our master equation. So P1, V1, N1, T1 equals P2, V2 over N2, T2. Well, we are just looking at the relationship between volume and amount. So we assume pressure stays the same. We're not going up or down a mountain, and we're assuming that temperature stays the same. You're in a conditioned room at like 32 degrees or 32 degrees Celsius, something like that. So we're looking at volume and amount. So Avogadro's law is V1 over N1 equals V2 over N2. Okay. The amount of gas affects the volume. So here we've got a problem, a 4.8 liter sample of helium gas. So we know our initial volume, V1, is 4.8 liters, contains 0.22 moles. So our initial amount, 0.22 moles. And it says of helium. Now, if instead of giving you moles, it had given to you this in grams, you would need to convert it into moles. Okay, so you'd have to use the molar mass to convert from grams to moles. So just make note of that. Amount cannot be in grams. So it would have to give you what the gas is in that case. This problem is asking you something slightly different than what the other equations have asked. It says, hey, how many additional moles of helium gas would you need to add to get to a final volume, our V2, of 6.4 liters? Assume a constant temperature and pressure. So we're going to have that V1 over N1 equals V2 over N2. Now, we're not actually solving for N2. N2 is the final. I don't know why I want to write vinyl. Is the final moles. But the problem is saying, hey, how many additional moles? So I want to figure out what the difference is between my final moles and the moles I originally had, right? I had a certain amount of helium already in there. So in this problem, additional moles, how many moles you added is going to be equal to your final, your N2 minus your N1, right? The final number times whatever the initial stuff that was already in there. So we need to figure out N2, our final moles, and then from there subtract out whatever the initial is. So N2, we want it by itself. N2 is going to equal N1 over V1, N1 times V2. Oop. Yeah, okay. Just making sure, all right. So N1 is the number of moles, 0.22 moles. I want to multiply that by my final volume, not my initial volume here. It's the final volume, V2. So we're going to multiply that by 6.4 liters. We're going to divide that by the initial volume, which was 4.8 liters. So my volume went up. So I expect the amount also to go up. When I plug this into the calculator, we got 0.22 times that 6.4 divided by 4.8. I've got a final amount of 0.29 moles. Okay, but it's not saying, hey, the final, it says how many additional moles. So I need to take my 0.29. I need to subtract whatever my initial was, which was 0.22. And I get a small amount, 0.29 minus 2. We get 0.07 moles of helium. We added 0.07 moles to get from here to our final volume. That's the only time I think really that you guys are going to see where it may be like a little tricky. So just notice, is it asking you to calculate the final moles, or is it asking you to calculate the additional moles? You'll solve it in two different ways. If it was asking you to solve the final, you could stop here. Okay, so that Grace and I'll chat with you about that after class. So all of those equations that we've done thus far have been a scenario where we have initial parameters and final parameters, right? There's some sort of change. So we heat the gas up, or we shrink the volume down, or we add gas. Now we're going to move to this thing called the ideal gas law. And the ideal gas law is you use it when you're sort of frozen in time. So there's not going to be any sort of change here. We are really just going to keep the pressure, the volume, and the temperature the same, and then solve for moles. This equation a lot of times is called Pivnert. PV equals nRT. So if you want to write this down underneath your notes for that master equation that we used, it's got similar variables, but there is something added to it. You can see this R thing. The R value is the ideal gas law constant. It doesn't change. So you know this thing. It's, you don't, but you will know it. It's 0.0821 moles, rather 0.0821, and it's got really funky units, liters times ATM per mole Kelvin. Okay, there are 4 things in this. And if you're like, why is that? Why are there so many units? Well, let's actually isolate for R. So if I take R right here and I get it by itself, that requires me to divide by N and T. So I would divide this side by N and T. Well, pressure is in ATM, volume is in liter, N is in moles, and T is in Kelvin. They don't cancel out. So that's why it has those funky units. Because R is in these units, that means that everything else has to honor those units. So pressure has to be in ATMs. Okay, so if the problem gives you something in millimeters of mercury, you've got to convert it. So make sure your pressure is in ATMs, make sure your volume is in liters. So if they give you milliliters, you got to convert it out. Amount of gas needs to be in moles, that's nothing new, and temperature needs to be in Kelvin. So when using the ideal gas law, all variables are restricted to these units. Now, when using PivNert, there's no change in. There's no like, oh, my initial pressure, my initial volume. It's saying, hey, I'm at this pressure, this volume, and I have this amount of gas. What is my temperature? Or I have this temperature, this amount, and this volume. What is my pressure? And you can solve for that. This equation, it has 1, 2, 3, 4, 5. It looks like it has 5 variables, but it really only has 4 because this is a constant, right? So you're going to be given 3 of the remaining things and you solve for the 4th. So let's look at a problem that would require the ideal gas law or PivNert. It says here, calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 ATMs and a temperature of 315 Kelvin. So we've got a gas, we know how much of it we have, we know the pressure it's at, and we know the temperature that it's at. And it says, hey, what's the volume? How do I know that I want to use the ideal gas law for this? There's no change in anything. My pressure is staying at 1.37. My temperature is staying at 315 Kelvin, and my amount is staying at 0.845 moles. So what I'll see students do sometimes is use this equation instead of using the change in equations, or using the change in equations instead of using this. So just make sure you use the ideal gas law when you're sort of at a specific state. All right, so PV equals nRT. That's our ideal gas law. Calculate the volume. So we want to get V. In order to get V, I got to move P to the other side. So we divide by P on both sides. That tells me that volume is going to equal the amount of gas times my constant times my temperature all over the pressure. Now, what is pressure in this problem? Pressure is 1.37 ATMs. Amount N is 0.845 moles. And temperature is 315 Kelvin. R, this thing here, is our constant. So have that written down somewhere. R is going to equal 0.0821. And the units again, funky, ATM times liter over mole Kelvin. This is a good reminder to just let you know, hey, make sure all these are in the units. So ATM, ATM, good there. Mole, mole, good there. And this is Kelvin, Kelvin, we're good there. So now we just plug and chug. My amount of gas, 0.845 moles. I add all my units, even for my R value. My R value is going to be 0.0821 ATM times liter over mole Kelvin. And then we multiply it by the temperature. And our temperature is 315 Kelvin. This whole thing gets divided by our pressure, which is 1.37 ATMs. Mole here is above the fraction bar. In this unit, it's below the fraction bar, so it cancels. Kelvin above, Kelvin in this case below. ATM above, ATM is below this fraction bar. So we'll just be left with units of liters, which is the unit we want for volume. 0.845 times 0.0821 times the 315. And then we divide it by 1.37. We get 3 sig figs everywhere. So the number I got in my calculator is 15.95. If I round to 3 sig figs, the 5 tells the 9 to go up, which would make this go up. So it should be 16.0 liters. You guys seeing how the ideal gas law is different in that it's sort of frozen in time. There's no change in. You want to be on the lookout for if it says, hey, I have this volume and then it changed to this volume, you want to use the first set of equations. If you're given just temperature, volume, sort of in this case, you want to use Hypnert. So I don't think it has any more examples in the slides. Let me give you guys some. We'll go back to partial pressures in a minute. So there's a nice worksheet in here that has all this stuff sort of mixed, jumbled together. We'll do a couple of them. I'll pick a couple out, but if you want some more practice with these sort of all clumped together, underneath the gas laws worksheet section, it's the second one. Yes. And it's nice too, because it has like all the equation stuff on the front page. So there's Boyle's law, there's Charles' law, Guy-Lassac law we didn't talk about, the combined gas law. It's got the ideal gas law, Hypnert. It also has this thing called Dalton's law, which we'll talk about in a second. It's got some of the abbreviations, some of the conversions. It's kind of everything from this chapter like smooshed together. So I'm not going to tell you which equation you need to use, how and where. Let's see. Do know though, on this worksheet, it does have Graham's law in it, which is the rate of effusion diffusions, how fast a gas will like spread out in space. We don't do anything with Graham's law for this class. If you go into 151, you might do a little bit with this, but we don't. So make sure just to ignore any problems that contain that, and do know that all the answers are on the back as well. So we're at the end. I'm going to do Guy-Lassac. Okay, so we'll do number 10 here. So as a sample of gas occupies a volume of 450 milliliters at 740 mmHgs and 16 degrees Celsius, determine the volume of this sample at 760 mmHgs and 37 degrees Celsius. I'm not going to tell you which equation you need to use. I want you to try and figure that out on your own. Set it up, isolate. We'll come back together at 7:13. We'll come back together at 7:20. So I'll give you 7 minutes to work on it, and also bathroom break and stuff like that. Okay, so first thing to tackle, probably the most challenging part, is to figure out just what you need to use for this. So I have some information here about volume, pressure, temperature, and it looks like we do in fact have a change in volume and a change in temperature. So this is going to be one of those V1, P1 equations. There are 5 pieces of equation of information here. So combined gas law is what I'm leaning towards, which tells us that P1 times V1 over T1 equals P2 times V2 over T2. The only thing that we don't reference in this problem is the amount of gas. I determine the volume. So we want to figure out the final volume. That means I need to move these 2 things over here. So isolating that, we'll go V2 is going to equal P1 times V1 times T2 divided by T1 over P2. If, and the way I did that, right, I'm going to multiply this by its inverse. So P2 on the bottom and T2 on the top to allow that to cancel and that to cancel. Whatever you do on this side, you do on this side. So we would also have to T2 this side. Okay, so P1, V1, T1, P2, V2, sorry, P2, T2. And then V2 is what we're trying to solve for. So I'm going to organize all my information. My initial pressure is 740 mmHgs. My initial volume is 450.0 milliliters. My initial temperature is 16 degrees Celsius. So right off the bat, I'm just going to add 273 to that so that I don't make the mistake of plugging that in 16 in the equation because it will give me the wrong answer. So 16 plus the 273 gives us 289 Kelvin, like that. So the second pressure, the final pressure, it goes up to 760 mm HGs, which is also 1 atm. And my final temperature, 37 degrees Celsius. Again, with this one, let's just add 273 to get it into Kelvin. So 37 plus the 270. That's 273. Gives us 310 Kelvin. Some people are like, oh, do I have to use the 273.13 or something? No, you can just use 273. It's close enough. So now we just plug it into the equation because we're looking for V2. So P1 is the 740 mmHg. The initial volume is the 450.0 milliliters. I can keep these in mmHg and milliliter because they're the same on both sides. The answer is just going to pop it out in milliliters, which is fine. Our final temperature, which is 310 Kelvin. We're going to divide that whole thing by the initial temperature, which was 289 Kelvin, and the final pressure, which was 760 mmHg. And kind of think about this too before I even solve for it. So my temperature is going up. Temperature going up means the volume gets bigger. My pressure is also going up, which means the volume is getting smaller. So I can't really calculate it that way. It's kind of a wash. 740 times the 450 times the 310. Not plug anything into my calculator today. Okay, so we get a final volume of like 469.996, something like that, milliliters. Too many sig figs, so let's round to, looks like temperature, we'll go 3 sig figs. 4, 6, 9, 9 tells this 9 to round up, so 470 milliliters would be our final answer. My care for sig figs drops pretty quickly this late in the semester. Just like you don't like sig figs, I actually also don't really like significant figures. So, but I have to teach it to you. Questions on this? On like what equation to use, why we use this one. Okay, we're going to do one more that I want you again to just go ahead and like go at it. I'm not going to tell you what equation to use. So we're not going to talk about STP yet, standard temperature and pressure yet. Looking for this very specific problem. Not going to do a fusion. Okay, let's do 15. It says, at what temperature in Celsius will 19.4 grams of molecular oxygen exert a pressure of 1,820 mmHgs in a 5.12 liter cylinder? I'll give you guys 5 minutes for that. Okay, so with this problem, we have information, well, we're given grams. Hopefully by this point, you can see that grams and moles are really interchangeable as long as you have the molar mass, if you know what it is. So I've got an amount value, I've got a pressure, and I've got a volume. I don't have anything about temperature. It wants us to figure out the temperature. There's no change happening here. So we don't have initial and final parameters. So this is a Pivner problem. PV equals N, not N, PV equals nRT, nRT. We are going to want to solve for the temperature component of this. So temperature is going to equal my pressure times my volume over my amount times my R constant. This particular equation is a stickler for units. So we need to make sure that we are in all of the units which R is related to. So let's write R out. R is our constant, 0.0821 ATM times the liter over mole Kelvin. So I have to make sure everything else is in these units. So my pressure is given to me as a 1,820 mmHgs. I need to convert that into ATMs. So I know that 1 ATM is equivalent to 760 mmHgs. I kind of just convert right in the beginning, so there's no risk of me plugging in something incorrectly. So 1820 divided by our 760, and we get approximately 2.39 ATMs. What else do we have? Volume is in liters, 5.12. So we're good there. Amount. Okay, N is currently in grams, 19.4 grams of O2. I don't want grams, I need this in moles. So 1 mole of O2, it doesn't weigh 16, it weighs 32 grams of O2. Why is it 32? It's a diatomic molecule, okay? That's why it says molecular oxygen, and it gives you the O2 formula. It wants you to multiply it by 2. So we're going to take that 19.4 and divide it by 32, which is the mass of 2 oxygens because they're clumped together, 0.606 moles of O2. And the last thing it wants, what we want to solve for is temperature. Right? It wants temperature in Celsius. Now, our equation isn't going to pop this out in Celsius. Our equation is going to pop it out in Kelvin. And then we can just do a quick conversion at the very end. So let's use this guy over here. We're going to take our pressure, which is 2.39 ATMs. We're going to multiply it by our volume, which is 5.12 liters. We're going to divide it by the constant, we'll divide it by moles, 0.606 moles. And then we are going to also divide it by the R constant, 0.0821 ATM, liter, mole, Kelvin. Okay, liters disappear, ATMs disappear, moles disappear, Kelvin stays. So we will just have Kelvin. Plug it in. Sorry, there's supposed to be a decimal here. 2.39 times 5.12. We divide it by the 0.606. You can equal that out, and then you have to divide it by the 0.0821. We should get a value of 246 Kelvin. Now it says, hey, I want degrees Celsius. So just take whatever this number is, subtract 273. So minus 273, and we get roughly negative 27 degrees Celsius. No, yes, did I do it incorrectly? I've been known to do that. Let me 39, I'll just double check. 2. Or 6. Yeah, no, we're good. Minus 273. All right. So any questions on this first part where we talked about the change in parameter equations like Boyle's law, Charles' law, Avogadro's law, or Pivner? It's just sort of, you're going to get some word problems and you got to make sure you pick out the right one, use the right one. There is a little bit left to this chapter I want to go over. So one thing to note, gases are not always acting ideally. So these laws that are like so neat, so nifty and convenient and clean and easy to use, it doesn't work in what we would call non-ideal gas conditions, which is low temperature when it's really, really cold, or high pressure where we've got a lot of like squishing together of the molecules. In these two situations, really cold or really high pressure, the gas molecules will start to interact with each other. They kind of clump together and the whole relationship falls apart as far as those nifty equations. So we really just use them in quote unquote ideal situations, which is where you are tested. That's sort of just FYI. All right, so partial pressures in a mixture of gas. So sometimes we have a pure gas like oxygen or nitrogen. Sometimes we have a mixture, which will have, the atmosphere, for instance, is 78% nitrogen, 21% oxygen, 0.9% argon, and a little bit of CO2. Well, the pressure due to any individual component in a gas mixture is known as its partial pressure. So nitrogen is exerting a certain pressure. Oxygen is exerting a certain pressure, and so is argon and carbon dioxide. When you add all of those partial pressures up, you get the total pressure of whatever you're looking at. If it's the atmosphere, then, for instance. So let's look at this mixture. We've got helium and neon gas. We're going to say that the overall partial pressure for this is 1 atm. So the P total, the total pressure, 1 atm. If the gas mixture is 80% helium and 20% neon, well, then 0.8% or 80% of the 1 atm, which would be 0.8 atm, is going to be coming from the helium. The helium is the majority of the pressure. The minority, the remaining 20%, is going to be neon. These two numbers, helium and neon's partial pressure, will equal the total pressure. It's like really basic equation. It just tells us whatever the total pressure is, it's equal to all the individual partial pressures. So if I gave you like the total pressure and two of the partial pressures, you could calculate the other partial pressure just by doing a very basic addition subtraction problem. If we look at air has a total pressure of 1 atm. 0.78 atms are coming from the nitrogen, 0.21 atms are coming from the oxygen, and 0.01 atms are coming from the argon. When we add those three things together, we get that total of 1 atm. So look at this problem here. It says, hey, a mixture of helium, neon, and argon gas has a total pressure of 558 mmHgs. So my P total is equal to 558 mmHgs. And this relationship will work for whatever units you're in. Just make sure that the units are all the same. So they're all in millimeters mercury, they're all in ATM, whatever. It says, hey, the partial pressure of helium is 341 mmHgs. The partial pressure for the neon, neon, is 112 mmHgs. It says, what's the partial pressure for the argon? The argon. So the equation for this tells us that the total pressure, P total, will always equal your individual things. In this case, I have three things. So I'm going to have P helium, the pressure of neon, and the pressure of argon, which is what we're trying to solve for. I can plug these things directly into this really, really basic equation, and we get 558 mmHgs is going to equal the 341 mmHgs plus the 112 mmHgs plus our P argon, whatever the argon is. So we just put in your calculator, right? So we'll take the 558, 558, which is the total. Let's subtract out first the helium. So subtract the 341. And then let's subtract out the neon, which is 112. And the remaining pressure, or P argon, is going to equal 105 mmHgs. Okay, the units stay consistent with whatever unit you are working with. Just note this number this number plus this number and this number need to equal your total. That's Dalton's law of partial pressure, really. I mean, problems can get trickier than that if I give you like percentages and things like that, but I'm not going to give you anything more complicated than this. Like on an exam, this is about the extent it's going to be. Okay, so if you can do that, you've got your partial pressure problem done. Other thing I want to talk about is STP. Okay, great. Pressure's a little more complicated in this problem. I'm not going to ask you about that. We don't do anything, just know we don't do vapor pressure. So give yourself a note so you don't have to stress about vapor pressure. If you take 151, you definitely will do vapor pressure, but just for time constraints, since we've got a couple other chapters to go through, I'm not going to worry about that. So ditch vapor pressure. We're also not going to do this, which is gases and chemical reactions. So PIVNERT, PV equals nRT. You can isolate for N. I'm just giving you the gist of what's happening. We're not going to actually do a calculation. Anytime you can solve for N, and remember N is moles. Anytime you solve for N, you can do stoichiometry if you have a balanced equation. So you pretty much solve for the amount of gas using these parameters, and you can figure out the gas of, or the amount of gas of a product. We're not going to do them. So hello and goodbye. But this we are going to do. STP. Okay, so STP is known as standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 1 ATM. Standard, meaning it's the same, right? Consistent temperature will be the 0 Celsius. Pressure will be the 1 ATM. It might not give it to you as 0 degrees Celsius and 1 ATM. It might say, hey, I'm at 273 degrees Kelvin and 760 mmHgs, and you would be able to derive from that you're at STP. But if you are at standard temperature and pressure, there's this super nifty conversion. 1 mole of any gas, doesn't matter if it's oxygen, helium, CO2, water, if it's in gaseous form, 1 mole of that gas will always equal 22.4 liters. Okay, just kind of a cool relationship. You could technically plug it into PIVNERT, like if you forget STP, you can plug PV equals nRT. It's just more work that way. I mean, you'd have to plug your 273 in for temperature and your 1 ATM in for your pressure, and you'll get the same answer, but this is just a really nifty conversion to use to kind of skip that. So let's look at 2 different gases here. I have helium at standard temperature and pressure, and I have xenon at standard temperature and pressure. If I have 1 mole of them, they will occupy the same volume, 22.4 liters, sort of this magic thing. How often are you given things in moles? Not very often. A lot of times you're given grams of gas. So if you're given grams of gas, you need to go from grams into moles, and then you can use that STP conversion. So I don't want to do it with stoichiometry. Let me give you guys something else. Okay, so we could say, what volume does 32.6 grams of neon occupy at STP? So if you see STP, you might want to just like automatically go to that idea. Okay, 1 mole of whatever gas I'm talking about, in this case it's neon, is equivalent to 22.4 liters. 22.4 liters. I'm not given moles. I'm given, sorry, let me put a little G there. I'm given grams. So what I want to do is I want to go from grams of neon, my little sort of thought chart here, into moles of neon. And then from moles of neon, I can really easily get into liters with that nifty conversion. Okay, so I've got 32.6 grams of neon. For every 1 mole of neon, oh my gosh, I forgot the molar mass of neon. You're slipping here. Usually I've got that whole chart memorized. 20.18. 20.18 grams of neon. That will get rid of my gram value, and now I'm in moles. Now I get to use this nifty STP thing. Don't use this if you're not at standard temperature and pressure. It won't work. you got to use pivnert then. So for every 1 mole of neon, I'm going to put that on the bottom because I want it to cancel. I get 22.4 liters of neon. Much kind of more slick than cumbersomely throwing it through pivnert. I get 32.6, times it by the 22.4, and then divide it by the 20.18. As far as sig figs are concerned, 3 sig figs, 36.2 liters. Okay. So I'm going to give you a similar-ish problem. Let's mix it up just like those. So how many grams of CO2 are in 13.5 liters at STP? Okay, I'll give you guys 4 minutes for that one. This one, you were given grams and I wanted volume. Here, I want grams and you're given volume. No, we're given grams and you want volume. Or flip-flopped here. You kind of work it backwards. All right, so this problem, again, you see STP, that's sort of indicating that we want to benefit from that quick relationship, which says 1 mole of CO2 will be equivalent to 22.4 liters. Now, this problem is going in the opposite direction. We're given a volume, so we know liters. I want to first get that into moles because that's all I can do with that relationship. And then from there, I can get it into grams. You guys seeing how this is the flip-flop of what we had up here. So we start with our volume this time, which is 13.5 liters. And using this relationship, well, I've got to put the liters on the bottom, and specifically it's liters of CO2. So we have 22.4 liters. That will be equivalent to 1 mole of CO2. Okay, liters will therefore cancel. We then can stitch together our next step, which is going from moles into grams. 1 mole of CO2 is going to go on the bottom because we want the mole and the mole to cancel. The weight of 1 mole of CO2 is approximately 44 or 44.01 grams. The mass of a carbon plus the mass of 2 oxygens. We then go ahead and plug in chug. So we take that 13.5, multiply it by anything that has value on the top that isn't a 1, so 44.01. And then we divide it by 22.4. We don't need to divide it by the 1 because it won't have an effect. And we'll be left with 26.5, 3 sig figs, 26.5 grams of CO2. So this is kind of a nifty thing to use if you're at STP. If you totally forgot about this ratio, but you remembered STP was 273 Kelvin and 1 ATM, you could also plug all this information into pivnert and get the number of moles and then convert it to grams, and it'll give you the same answer. This is just a little faster, I think. So that, my friends, is it for gas laws. A lot of, not even a lot, just equations. You have your equations, have those couple little details about like Dalton's law and STP. I do think that one worksheet is helpful. So this guy here, especially that front page, is just a really nice way to sort of consolidate the entire chapter on one page, which anytime you can do that, that's helpful. Okay. So we are not meeting next week because it's Thanksgiving. So I will see you all in 2 weeks. No tests between now and then. Keep an eye on your homework / lab due dates. Just honor whatever's on the syllabus. And I'll see you guys in 2 weeks. And then we're just going to really plug and chug and get through it. And then we'll be done. Yay. So if you have any questions, general, throw them out there. Personal, stay around. And I will see you guys in 2 weeks. Have an awesome, awesome Thanksgiving. Eat and drink lots. Bye, guys. Bye, Cynthia. Thank you. Hey, Grayson.
Hey, I was just